Well, we're going to be talking about low tox next, or actually we're going to talk about a couple things, but I'm going to put everybody else but Naresh Suchak on mute at this point in time. I'm going to mute everybody, and then we're going to unmute Naresh. And Naresh, just make sure that I can hear you. You want to acknowledge your presence?
Yeah, this is Naresh Suchak from Linda Gas.
Okay, good. We're all set then. So we're going to go back into share my desk. I'm going to talk about a couple other things for a minute, and then we'll talk about low tox. But Chris had mentioned the hydrochloric acid, and one of the potentials that we think is huge for the power industry is to use the Illinois Basin high chlorine coals and generate hydrochloric acid. And we've been showing this pictorial here for the last 4 or 5 years. Our understanding now is Hitachi has actually patented a process to make hydrochloric acid along with gypsum from power plant flue gas, and that it is now commercial. It is being used. As this is not, our recommendations was not because of our own invention, but because just this is what incinerators in Europe are doing, and why not do it with power plants in the U.S. But particularly with the mercury now, the advantage is you're not only are making the 30% hydrochloric acid, but all your mercury gets captured and concentrated in your ion exchange resins, and we think that this is a big point value in that it isn't in your fly ash along with the carbon, it isn't in your gypsum that goes into your wallboard, and it all ends up in one place. So we do have information on this, and as I say, Hitachi's actually patented a system now. And another variation on the chlorine is the Skyonic process, and they just got some substantial new funding, and they have been a presenter in our CO2 webinars in the past, topic hours. But they start with salts, and then they separate it into the sodium, and so they make the chlorine as an end product, and they end up with the sodium, which they then use to react with the CO2 to make sodium carbonates. And the fact now that there's substantial new funding, I think makes us want to take another look at them as well. So that's another thing that's in our bank of information. But now let's move on to a technology that, we're going to be looking at low tox, but EcoPower is also out there talking about using ozone for NOx and mercury removal. So BOC is now part of Linde and has extensively investigated this potential. And with us on the phone is Naresh Suchak of Linde. Naresh, you want to give us a little bit of your background, if you would, please?
Yeah, I'm with Linda BOC Linda for last 12 years, and have been working with NOx removal and other environmental technologies. This low tox, this low temperature oxidation process that was developed at Linda or BOC, and we have used this on many different gas streams, and we have whole process fitted on a trailer that it can be taken from place to place, and we can hold a demonstration on a slipstream, and every single demonstration has been successful up till now.
And you've shown some of the benefits and things here. If you just kind of summarize where this stands as you're displaying it on the slide here.
Yeah. Low tox is basically a good NOx control technology that could be integrated in any dry or wet scrubbing system, and it is very effective on a dirty gas, dirty in meaning having a particulate matter, and other pollutants like HCl, HF, any acid gases. And after oxidizing this stream, we capture in wet or dry scrubber. It is in particularly suitable when you want NOx removal in excess of 80%, 90%, because it costs more than the low-end technologies, but it's comparable to SCR and high-end technologies, where you require stack emissions of 20 ppm or in that range. Co-benefit is that it also oxidizes ozone, also oxidizes mercury to some level. In different investigations, we have found between 30 to 80%, whereas NOx removal was in 60 to 90%. We got mercury oxidation in 30 to 80%, depending on how much is the elemental mercury and other things. Commercial installation was done on 25 megawatts coal-fired unit, and we have shown that we can bring down NOx emissions to 5 ppm and 10 ppm on continuous basis. For months of demonstration data was available. In this presentation, we have shown at least 1 day, 24-hour data of NOx removal. And this technology has been very, very widely accepted on now FCC regenerator off gas, where almost like half a NOx pollution from a refinery is from FCC regenerator, and low-tox has been retrofitted in 25 FCCs in U.S., China, and recently now we also have got order from Thailand. And integration is very simple. You have a combustion source, and you have a scrubbing device like wet FGD or dry FGD. And go next. We introduce ozone. Ozone is made from oxygen by flowing through a corona discharge, where electricity is applied or high voltage is applied. So oxygen, part of oxygen gets converted to ozone, and this ozone-containing oxygen stream is injected in the flue gas. Can you go next, please? NOx is oxidized to NO2, and NO2 is then oxidized to N2O5. NO is almost insoluble gas, and that is why it does not come out in wet scrubbing, whereas N2O5 is almost infinitely soluble, and almost all NOx comes out. Whatever N2O5 is formed, it comes out. While oxidizing NOx, ozone also oxidizes part of mercury. Mercury oxidation is slightly slower because of low concentration, and so mercury removal or mercury oxidation is co-benefit of NOx oxidation. CO and SO2 oxidation are very, very slow, 100-fold or 1,000-fold slower, and you do not see much consumption of ozone even with elevated levels of CO or SO2. And as I said, N2O5 is soluble in all proportions with water, and you get HNO3. Now, this HNO3 is neutralized with whatever scrubbing media you have, sodium, potassium, ammonia, limestone, anything. And it is not sensitive to pH, so you can be scrubbing with a water at 2 pH, and still you can remove almost 98-99% of NOx. Here is a picture of 25 megawatt coal-fired power plant, and you can see the duct that takes the flue gas, to the wet scrubber. Wet scrubber is shown on the right, and you can see the water scrubbing media injection pipes, and below that there is a small scrubbing section. Section above that is empty almost, and this was operated by Linda for 6 months as a part of agreement. Can you go next, please? And here you can see the NOx emission was maintained at 5 ppm up to 7 o'clock. At 7 o'clock, the set point was changed to 10 ppm, and then 24 hours run was at 10 ppm. So we ran the system at various levels, varying various conditions, pH, and all ppm NOx at outlet, and we had absolutely consistent performance. This was on automated control on full scale, and we collected data for over a month in our computer. Next, please. At present time, in the initial stage, we installed this system on 400 HP gas-fired boiler, stainless steel pickling unit, which is still operating, 25 megawatts coal-fired boiler. Then lead recovery furnace, that's also over 10 years now since installation. We also installed on 1,000 HP natural gas-fired boiler in downtown LA, and that was installed in 2001. After that, we focused a lot on FCC regenerator. In the initial stage in 2007, we had 5 FCCs come online same time, almost in the same year, 2007, 2008. Then in 2008, we put in treating sulfuric acid exhaust. There were 2 plants, and both plants were retrofitted with, fitted with NOx control using low tox, and that's been operating since 2008. Then now we have, I think, 8 or 9 FCCs already signed in U.S., and another 8 or 9 in China. This presentation is a couple of months ago, and we have 2-3 additional, so that's why we have approximately 25 probably installations of FCC for low tox, and we have done 12 demonstrations on various flue gas, such as glass furnace flue gas, then waste incineration. We have done on biomass boilers, and number of coal-fired boilers, all types of fuel like lignite, petcoke, and every single demonstration has achieved what was put as a success criteria, and invariably success criteria is 90% or more NOx removal.
It's very impressive. What strikes me is the huge potential to upgrade plants that already have scrubbers and may even have selective catalytic reduction systems already installed, that since you have the scrubber, all you really have to do is inject the ozone ahead of it, and you're going to greatly improve the efficiency. And if the plant has little space, if it already has an SCR installed, and there isn't room for adding additional beds, then the cost to go from 98% to say 95% removal could be very substantial by expanding, by putting in a whole nother catalyst system or adding several different beds. Where here, and all Bob,
one of the main thing is to not complicate air pollution control system, which already all these manufacturers or all the producers of chemicals or power, they already have a lot of air pollution control equipment. So what we thought, what our philosophy is, that can we use what is already on the ground and without complicating their air pollution control so that they can focus on what they do for as a prime objective, like power producers want to produce power. So how can we help them in not complicating their APC? So here what we are doing is introducing ozone, which does not cause any pluggage. Ozone is produced on site, on demand. It's a very oxidative chemical, very reactive chemical. So you don't want to store, I mean, you can store and you don't store in this process, and you convert almost insoluble gas into soluble, into highly, highly soluble using the existing acid gas particulate removal or SOx removal scrubber. We have tried all different types of scrubber, and every single scrubber removed 99 to 99.5% of NOx that is in form of N2O5. So just to give you an example, in the FCC, 100,000 barrels, typical FCC of 100,000 barrels a day. Now, if you put SCR or if you put any technology that obstructs the flow, and if they have to even take a shutdown for one day, $100 billion, I mean 100,000 and $100 a barrel, it's a $10 million production, this thing. So what we came up with is that we provide them a solution which does not any way obstruct what they do upfront, in whether in heat recovery or in processing, and we have technology that goes with existing air pollution control equipment. That's what our philosophy.
And it should be particularly attractive to a lot of these older plants that are concerned that, you know, putting a lot of money into new SCRs and might might be unproductive from the standpoint that closing the plant down in 10 years. Here they have a way to do it without that.
And absolutely. And if you have, let's say, 5 scrubbers on say 2 gigawatt power plant, you have 4, 5, 6 scrubbers. Now you can implement in 2 or 3 scrubbers, but you can pipe ozone to all 5. So you can implement this technology in stages if you want to. And second thing is, if you decide, if it's a very, very old plant, and if you put ozone generation capacity, this capacity can be skid mounted and taken to another plant if you have to. So
this offers the opportunity really for some sort of a contract, you know, for that where the power plant may not even have to make the capital investment.
Exactly. Yeah. In case of stainless steel pickling and lead recovery furnace, they're already our gas customer. We sell industrial gases. We sell approximately 19% of all worldwide industrial gases. And stainless steel pickling and lead recovery furnace, the system of ozone generation and gas supply, they are on lease basis, so they pay as they go. So customer doesn't have to, in that case, put a capital, and capital is then depreciated over 15 years of time.
Well, that's very interesting. Let's open the session, see if there are questions from the floor here.
Sure.
And let's see, maybe I didn't hit that unmute all. Unmute all. Okay, why is everybody not being unmuted? So unmute all. Okay. Doesn't want to seem to unmute everybody. Why is that? Okay. Unmute all. I'm doing what they said we should do here, and we're still not. everybody is, I guess there we got everybody unmuted. So questions from the floor.
Jerry Radwood.
Yeah, Jerry.
One is, you're dissolving the nitrogen compounds in the scrubber. What happens there?
It forms a nitrate salt.
And
yeah.
It doesn't pose any problem in ultimate disposal or bleed streams, or is it what's the ultimate?
Nitrate is consumed, at least in refineries, in the effluent treatment plant, because they have a lot of organics, and in anaerobic section, the bacteria eat up nitrate to remove the organics. So that is advantageous to them. And in gas-fired boilers, the quantity is so small that it's handled by wastewater treatment.
Nitrate's terrible in water discharge. You have to take care of it.
Yeah, if you have to take care of it, for example, we did feasibility for very, very large scale power production. Then one of the in one situation, they wanted to make ammonium salts of nitrate along with ammonium sulfate, which makes a fertilizer. Another case study we did, they wanted to separate calcium nitrate from the scrubber FGD water so that they can sell that as a byproduct. But these are at very, very large quantity. A small quantity, you would treat it in wastewater treatment.
The other question, very little conversion to S3.
You're breaking up.
Yeah, I think we're going to have to start. Well, in fact, Jerry, you're going to be the next speaker, so I think what I'm going to do is we'll actually clear that up. I'm going to put everybody else on mute here, mute all, and then I'm going to unmute Jerry. Yeah, and Jerry, what was your question again? And we'll get this answered maybe after your presentation.
The question was about oxidation of the SO2 to SO3, because the ECHO folks are depending on that conversion to capture the sulfur as acid.
Okay, that sounds like a legitimate question. We'll get an answer to that after we hear your presentation. And so we will go to it and then get back and get Naresh's comments after you finish, and we get comments from on both topics.
Okay.
So, why don't you give us your presentation at this point in time?
Okay.